In this video, we're going to introduce the idea of the standard normal curve. So Chifaru, besides being a big nerd, she and her mother are huge baseball fans. Baseball talks a lot about statistics, and she noticed how a lot of the statistics, they show a mound-shaped distribution if you look at a histogram of the players. She also remembers from earlier in the class that mound-shaped distributions, they tend to follow something called the empirical rule, where 68% of the data is between 1 and 2 standard deviations above and below the mean, 95% is within 2 standard deviations above and below the mean, 99.7 is within 3, etc. And she also knows that the z-score that we calculated can tell us exactly how many standard deviations away from the mean every particular data point is. So if we know all of this information about things that have this mound shape, she wants to know what else we can learn about this common shape and particularly data points in it. So let's look at a histogram of, say, the batting average in 2016. If we look at it using the relative frequency, and particularly a relative frequency as a decimal, so this is 0.00, 0.02, 0.04, 0.12, 0.10, 0.08, 0.06, etc. Then if we add up the heights of all of these bars, they all add up to 1. So the area under these blocks adds up to 1. And the heights of the bars tell us the probability that a randomly selected data point, in this case a randomly selected player, is going to be in that class. Now, batting average in 2016 kind of showed this really nice mound-shaped, right? We got a little tail here, we got a little tail here, and we got a big bulge in the middle. And we can use you can use an approximation of this with a nice smooth curve and talk about how that goes in the next slide. So if we take our mean and our standard deviation, right? Our standard deviation was 0.027. We can build a nice smooth approximation to our histogram, okay, with the mean in the center and the distance from the mean to 1 standard deviation above is 0.27. This curve that we create is then going to be our standard normal curve, which means that about 68% of the area is going to be between 1 standard deviation below and 1 standard deviation above. If we look at the total area under the curve from 2 standard deviations below and 2 standard deviations above, that's going to be about 95%. And if we look 3 standard deviations below and 3 standard deviations above, the total area under the curve is about 99.7%. One of the nice things about using this curve is that if I add up the total area under the curve, this total area is equal to 1, right? There's an area of 1 under this curve if I take it all the way out to infinity on either end. And if I want to know the area between 2 values, say A and B, right? Because this is a really nice understood curve, this area that I can calculate is the proportion of the population that's between the A and the B that I've chosen. And it also tells me that what the probability that any random data point I choose is going to be between A and B. So if I can find these areas in between A and B using this really well-known curve, it'll tell me these 2 things. All right, so what can we do with this? So if the total area under the curve is equal to 1, if I have some point A, that means 1 has to be equal to the area less than A and the area greater than A. So if I know one of these things, I automatically know the other one. Because the area greater than A, which I might be interested in, well, it's going to be what's left over after I take away the area less than A. And if I want to know the area between 2 points A and B, what I can do is I can use the area less than B and simply take away the area less than A, and that'll be the part that's left over. So in practice, I really only need to know the amount of area under the curve less than a particular value, and I can calculate greater than or in between. And this is how most of the tables are created. Now, a normal curve is defined by the mean and the standard deviation in this mound-shaped distribution, right? The mean is going to be in the middle, and the standard deviation is going to tell us where these distances are. Okay? So if I know those two things, I can create a nice normal curve around my data and use that as my approximate calculations. Right? The normal curve it's the basis of this empirical rule, right? We have this really nice curve here, and that's the thing that tells us about the 68, 95, 99.7. In standard tables that we use, they use the z-score because any particular normal curve for a particular data set is going to be centered around the mean for that data set. So what we really care about is we use the z-scores to be able to use the tables for any particular data set. Okay? And most of these tables will give the amount of the curve that is less than a particular z-score. Not all of them, but most of them, right? So you're going to find some particular z-score, and the table will tell you the area left of that point. Next, we're going to do some quick calculations. In class, I'll show you how to get the probabilities. All right, so let's do a couple examples using our batting average data from 2016. The mean was 273, and the standard deviation was 0.27. These are the things that are going to go into our z-score calculation. All right, so Chief-Aru wants to know what portion of the baseball players batted less than 265. All right, so let's set up our z-score. Remember, it's the data point minus the mean divided by the standard deviation. So in this case, it looks like this. Our data point was 265. That's the point we worry about. The mean was 273, and the standard deviation was 0.27. All right, do a quick calculation, and let's see what we get. All right, so I get a z-score of negative 0.30. Most of the tables that we're going to see, they only use z-scores up to the 100th place, so it's the second decimal place, so let's leave that where it is now. Okay, so if we want to know what proportion of the baseball players batted less than 265, we can use our approximation with the standard normal curve as follows. Right. So the probability that a data point is less than 265, a player bats less than 265, is also the probability that a random z-score has a value less than negative 0.3. Okay? Now, we go to the table, we can use a calculator, and what we get is the following. Right? We get a value of 0.3821, right? So about 38.21% of the players batted less than 265 in this data set. In this case, I read this from the table in the back of the book. Most of them are pretty similar. Right, so I said that these tables give z-scores for the less than, but can we figure out greater than, right? So, well, what's the probability that a randomly selected baseball player hit higher than 290? So we're going to use the complement piece here. All right, first we need to know our z-score. 285 minus 273 over 0.27 gives me a z-score of 0.44. So what this means in terms of the probability, right, the probability that a data point is greater than 290 is the same as the probability that a z-score is greater than 0.44. Now, the tables give us the data less than, so we want to use 1 minus the probability that z is less than 0.44. And this we can get from the table or the calculator. So in this case, the probability that a z-score is less than 0.44 is a nice round number, 0.6700. Right, so 1 minus that is 0.3300. Right, so there's a 33% chance that a player hit higher than 290 based on this normal curve. Well, what if we want to know about between, right? Here we have an A and a B, and we want to know the part between. Well, we find the part less than the higher one, and we take away the part less than the lower one. And what we're left over with is the piece that we want. But first we need to know the z-scores for both of these things if we're going to use our table. So let's do those calculations. All right, so for the first one, let's go with 250 as our low end. So our x value is 250, the mean 273, the standard deviation 0.27. This gives me a z-score of negative 0.85. For our other z-score, we want to know 270. Our mean is 273. Our standard deviation is 0.27. This gives me a z-score of negative 0.11. So both of our z's are less than our mean in this case. We want to know the area between. All right, so again, the probability that a random player hits between 250 and 270 is the same as the probability that a randomly selected z-score is between, oh, those are on the wrong side. Oops. This should be negative 0.85. That's the lower one. And negative 0.11. Now, nobody's perfect. Okay? All right. Here I did it the right way. I have 0.11. That's the one closest to the mean. Right? There's our mean. This is 0.11. 0.85 is that one. So I'm taking the higher one, and I'm taking off the lower one. If you look on the tables, the probability that a z-score is less than 0.11 is 0.4562, right? So there's a 45.62% chance somebody hits less than 270. There is a 0.1977 chance that a random z-score is less than 0.85, which is the same as saying there's a 0.1977 probability that a random baseball player hits less than 270. This difference is our gap in the middle, and that is 0.2585. A little more than 25% of the players hit between 250 and 270. Okay? All right. So let's do it right, and I will see you in the next class.